Welcome, ladies and gentlemen, to this video lecture. Okay, so let us discuss the product law for limits. So, with a, l, m, f, and g as before, if the limit as x tends to a of f of x is equal to L, and if the limit as x tends to a of g of x is equal to m, then the limit as x tends to a of the product of f of x and g of x is equal to the product of L and m. Okay, so let us prove this. So what I would suggest is you pause this video here and you first write out your proof outline. And then you unpause the video and then you see how it compares to the one that I will write down now. So pause the video and try it out first. Okay, let's write out our proof outline. Proof outline. Okay, we want to prove this implication. So we will assume the hypothesis. So we will assume that the limit as x tends to a of f of x is equal to L, and the limit as x tends to a of g of x is equal to m. Then we want to prove that this limit is equal to L times m. And so what do we need to prove? I'm not going to write down the exact statement of what this means. I will leave that as an exercise. I'm just going to go straight into writing the proof outline. We want to prove for every epsilon. So we fix any epsilon greater than 0. We want to define a delta. We have to show that there exists a delta, so we should define it. Define delta as something, as long as it's bigger than 0, so that under the assumption, so assume that 0 is less than x minus a, is less than delta. Here we want to do some work, and in the end we want to have that f of x times g of x minus L times m is less than epsilon. So here is our proof outline. So this is what we need to fill out. So here is our scaffolding. And now, of course, here we have little shops. We have two shops again, where we can, if we have the right epsilons, we can go by the correct deltas. Okay, so here we've got our proof outline. Let us jump into writing our proof. So I'm going to, perhaps it is a good idea to duplicate this page and write our proof. So when we start off, we don't really know where we want to go, except that we want this expression to be less than epsilon. So let's start there. So what I'm going to do is I'm going to erase all of this. So this is our proof for realsies. Take this guy, move him over there. Okay, let us manipulate this thing a little bit. And now we're going to do the same trick that we did or that we have seen a couple of times before. We're going to add 0 and apply the triangle inequality, but we're going to add a very special 0. You will see. So this is equal to f of x times g of x, and let us subtract L times g of x, and we immediately add it back. L times g of x minus Lm. And let's put brackets like so. And now let's factor out everything that we need. So let's factor out the g, so g of x f of x minus L, and let's over here actually I'm skipping steps here. So first what we're doing is we're applying the triangle inequality over here. Like so, plus L g of x minus Lm, and now let's factor out what we can factor out. So this is equal to, factor out the g in the first term, g of x, f of x minus L, plus, and let's factor out the L, g of x minus m. And now you see here, over here we have something that we can control, and over here we have something that we can control. These expressions occur in the definition of these limits that we are assuming exist. So if we call this again shop A and shop B, we can get deltas which work for these expressions. So let's see, how can we do this? There is something wrong here. Here I made a mistake. This should be absolute value of L. L could be negative. Okay. So here we don't have a problem. Here we don't have a problem because here we have a constant times something that we can control. So if we control this guy, and if we get this guy to play well with that L, we can get this less than, for example, epsilon over 2, as before. Here we have a problem. We would like to control this factor. This we can control. We can, by choosing things appropriately, we can use this assumption to control this factor. But here we have a problem, this g of x. So let us think how we can control this g of x. What control do we have? The only control that we have is that this limit exists. Okay. So maybe what I'm going to do is I'm going to take this part and I'm going to move it down because I need a bit more space. Cut and paste. Good. First of all, let us see how can we control this guy. So the if we can get this guy to be less than or equal to some constant, then we can use what we know for this expression to get rid of this constant. So let's think about how can we get this absolute value of g of x to be controlled by a constant. And we will use shop B. So firstly, so let's call this 0.1. Let's make an epsilon. Let epsilon 1 be equal to 1. And let us go by a delta at shop B. So from B, there exists a delta 1 greater than 0, so that if, or let me write it over here, if 0 is less than x minus a is less than delta 1, then we have g of x minus m is less than epsilon 1, but which is equal to 1. But we're not interested in this, we are interested in that. So let's see here. Let's keep this in mind. So let's say under this condition, under condition 0 is less than x minus a less than delta 1, g of x, this is what we're interested in. Let's add and subtract an m, g of x minus m, and we immediately add it back. Triangle inequality, g of x minus m plus m, and this is less than 1 plus m. And here we see, we can get this thing to be less than 1 plus, oh, and again I forget the absolute value. And that is, m can be negative. So you must have the absolute value. So under this condition, we can get g of x to be less than 1 plus m, which is just a constant. So that takes care of this term. But okay, so now we should bake in a delta 1 into our delta. So let me rearrange this a little bit so that we have more space. Like so. And then if we bake in a delta 1 into our delta, what we have then here is that then 0 is less than x minus a is less than delta, which will be less than or equal to delta 1. And then here, since let's just say let's call this star or by star g of x is less than or equal to 1 plus absolute value m of f of x minus L plus absolute value of L times g of x minus m. Okay. Okay. So now we've taken care of this niggly little factor over there, which depends on x, which we wanted to be bounded by a constant. Now we have bounded it by a constant. Okay. Now we are ready to go by deltas to take care of these guys. So remember, what do we want? We want finally, in the end, we want this thing to be less than epsilon. So this thing, we want finally to be less than epsilon over 2, and this thing also less than epsilon over 2, so that when we add the two together, we get epsilon. That is what we want. So now we must construct deltas, which will work for this term and for that term. Okay, let's see how we can do that. Okay, and let's call this number 2. Let us find a delta that will work here. So we've got our epsilon that we fixed here. Let us define epsilon 2 as what? We want this thing finally to be less than epsilon over 2. So, and this thing, that should be epsilon over 2 multiplied with 1 plus absolute value of m. Because we see here, if we can get this thing less than that, the whole thing then simplifies to epsilon over 2. Okay, and now for this epsilon, we go by a delta. So by A, there exists a delta 2, so that if 0 is less than x minus a is less than delta 2, then f of x minus L is less than epsilon over 2, which is equal to not epsilon over 2, epsilon 2, which is equal to epsilon over 2 multiplied with 1 over 1 plus absolute value of m. Like so. So under this condition, this thing we can get less than epsilon over epsilon 2. So under the condition that this thing is less than delta 2. So we got to bake in a delta 2 here. And we so that we automatically get this delta should be less than delta 2. Let's call this double star. So here by star and 1 we get this. And now by double star and 2, by double star and 2, this is less than or equal to 1 plus 1 absolute value m, epsilon over 2, 1 over 1 plus absolute value of m. That cancels with that. And what are we left with? L g of x minus m. Okay, halfway there. This is equal to epsilon over 2 plus L, absolute value L, gx minus m. Good. Now we just need to take care of this one. So we go back up here. I need a bit more space, so I'm gonna move this back down. And gotta move this down a bit. That is that enough space? Maybe let's decrease the size of this. Resize, like so. Let's call this number 3. Now define, what do we want? We want this thing, or this whole thing, we want to simplify to epsilon over 2. So this thing we have control over. So let's define epsilon 3 to be epsilon over 2 multiplied with 1 over L. Hang on, there's a problem. What is the problem? What is the problem? The problem is L could be 0. Not allowed to divide by 0. How do we solve this problem? There's a really simple solution. We just say 1 plus absolute value of L. This is non-negative. In the case that it is equal to 0, then this adding this 1 takes care of that. And 1 plus absolute value of L, that is strictly bigger than absolute value of L. So that will, if you take L divided by 1 plus absolute value of L, that will give you a number that is less than 1. So that will do. Okay, Now, at which shop are we going to buy a delta? We're going to buy a delta from shop A, right? No, shop B. This has to do with the G. So from shop B. So by B, there exists a delta 3 greater than 0, which works with epsilon 3. So that if 0 is less than x minus a less than delta 3, then g of x minus m is less than epsilon 3, which is equal to epsilon over 2, 1 over 1 plus absolute value of L. So under this condition, we get what we want. So we got to bake in a delta 3 into our delta. Take the minimum of all of these. Since we take the minimum of all of them, we get the following. If we assume that, but delta is constructed to be smaller than all of them because we are taking the minimum. So delta is less than delta 1, delta is less than delta 2, delta is less than delta 3. Let's call this triple star. And now here, by triple star and 3, we have that this is less than epsilon over 2 plus 1 over L. What do we get? Epsilon over 2 multiplied with 1 over 1 plus absolute value of L. If we rearrange a little bit, epsilon over 2 plus L over 1 plus absolute value 1 plus L, epsilon over 2. This guy is less than 1. Exercise. Show that that is true. That's not particularly difficult. So this is less than epsilon over 2. And in fact, what we have here is strictly less than, because this is strictly less than that. This is strictly less than that. So we've got strictly less than, and here we've got less than or equal to, because this is less than or equal to 1 plus epsilon over 2, which simplifies to epsilon. And there we are done. Okay. So let's go through this again. Just to recap. We want to prove the product law for limits. We want to show if the limit of f of x is L and the limit of g of x is M, then the limit of f of x times g of x is L times M. So we assume the hypothesis, and we want to show that this limit holds true. So we have to show that it satisfies the definition. We have to show for every epsilon, so we fix any epsilon. Then we use our assumptions to construct our delta, and we use it 3 times to construct our delta, like so. We assume that 0 is less than x minus a less than delta. This gives us automatically that from our use of our assumptions, that these conditions in that we use to construct our delta are automatically satisfied. And this gives us, first of all, that we can control this factor over there by star and by 1. So by star, where did I put star? By star and by 1. So by star we've got this thing is less than delta 1, and by 1, if this thing is less than delta 1, then we get g of x in absolute value less than 1 plus m. So that is how we get this. Then this thing is less than epsilon 2 over 1 epsilon over 2 times 1 over 1 plus absolute value epsilon by double star and 2. So double star is here, tells us under this assumption this is true, this thing is less than delta 2, but 2 tells us if this thing is less than delta 2, this thing f of x minus L in absolute value is less than epsilon 2, which is how we defined it over here. So we get this thing is less than that thing. And then finally, over here, by triple star is here. So from this assumption, we automatically get this assumption, or that this is true. And since this is true by 3, over here, we get that this expression is less than epsilon 3, which is defined as that. So over here, we get that by triple star and 3, this thing is less than that expression. Put it all together, simplify, we get that everything is less than epsilon, which is what we wanted. So here we have proven the product rule for limits. Let me again reiterate, I do not think that this is easy, especially the first time that you see it, but the more experience that you get, the easier it becomes. There is this famous quote, let's see if we can find it. I think it is by John von Neumann. You don't understand mathematics, you just get used to it, which I think is applicable over here. Let's see if we can find it. Understand mathematics, used to it. Let's see. Quote by John von Neumann. Young man, in mathematics you don't understand things, you just get used to them. So I think this is a particular case of how we get used to things. Okay, so that was the proof of the product law for limits. I will see you in the next one.